In preparation to get the printer working, I decided to measure out what the original signals look like, so know the timing for the motors and stuff like that. I was just looking around the board to see, so that the motors usually the stepper motors are just driven by these ULN 2003 Darlington transistor arrays. So very simplistic driver, everything's done in software. It's going to be easy to replicate. I ordered a couple of the ULNs, so I will replicate the circuit as is. Since I know it will work, that's going to be the easiest, and I'm going to drive it using a microcontroller. So for now, to trace it out, I thought, okay, I'm going to just take a logic analyzer and look at this stuff. Okay, the recording of the carriage stepper is done. To record other waveforms, like how they use the hammer and stuff, I need to hook the keyboard back up, which I will do in just a second, and then I probably won't hook up the motors. I don't really need this for the logic waveforms, but I need to hook that stuff back up the keyboard so I can enter the right mode. I just did the recording of the stepper waveforms for the carriage movement, and as I said, probably the ones for the other steppers don't look different. So I'm gonna go with these for all, and if it doesn't work, then I'm gonna investigate further. I'm trying to not destroy the board yet, the original board yet, because there might always be something that I want to look up, like timings and stuff like that. So I'm trying to keep that alive as a fallback solution. Anyways, I'm gonna try and replicate this waveform for the printer then. And yeah, it looks very, very simple. Your standard stepper motor driving waveform with two signals 180 degrees out of phase in pairs, and then these two pairs are 90 degrees out of phase, or if you want, we can rearrange it to be the nice stepping pattern here. So this is what I'm going to replicate with an AVR. Very simple. It's only 4 to 5 milliseconds here, so you can see pulse length. Should be very easy to generate, even if the AVR has a lot of other stuff to do. There's this kind of weird startup behavior here. I'm not sure what this is. I guess it's just a glitch. It could be something to, what do I know, align the motors or something. I'm not that familiar with stepper motors, but I don't see how this should help. So I'm just going to leave this out. I think this is just some startup glitch of the microprocessor, because it's doing a lot of other stuff in there. I don't know what to do in there. I'm just going to try this, and we should be okay. Yeah, as I said, it might be something with aligning the motor, so we have an absolute position to start out with. But then we've got this weird startup waveform here as well, where one pulse is suddenly longer, and then we go to the normal waveform of driving it. Yeah. I want to just quickly talk about the different inputs to the printhead here, or to the general print assembly, which we have. So I'll just start on the left and go through different connections. So first of all, there is this one here labeled IND-CA. That's the left limit switch. So when a carriage moves to the left, it can detect when it reached the end of the rail. Then next is a stepper motor connection labeled LF, which goes to a motor here in the back, which just simply drives the paper feed. The next one is labeled CA for carriage, which controls left-right movement of the carriage. The one after that is labeled WH, which controls the daisy wheel. Then we have 3 DC signals. This one here is labeled RI, and it is used to arm the hammer. What that means, I'm going to tell you in just a second. Then we've got the blue connection, which is labeled CO. That one is to enable correction, so also to arm correction, let's call that. And then we've got one here labeled DC, and that is connected to a simple DC motor inside the assembly. Now to switch to actuate the hammer, we actually have to enable the DC motor, so it needs to be constantly running. And if we then pulse this connection here, which is connected to a simple solenoid, it releases the hammer. So basically you can imagine the motor winding up a coil, and this will release it. Same for the correction. It triggers a solenoid which moves the whole tape assembly up, so the so that the hammer will now hit the correction tape instead of the normal tape. And yeah, that's a basic rundown of how to control this carriage. I just took a look at the motors, and they all appear to be the same from the outside. They might be different, but let's just go with that. They're all the same type. So I only needed to record the waveforms from this one motor. For the other signals, those two are the solenoids, and this last one here is the DC motor. The DC motor waveform, well, that's not hard to guess. Like, it's just turning it on and it's going to run for a while. This one over here is just the switch input from the limit switch. That's also like, yeah, it's a switch. But what I'm interested in is how they control the solenoids, not specifically the on duration that they use to drive those, but I'm more interested in the maximum interval that they use it, so the maximum typing speed I can get out of this machine. Another thing that might be interesting, but I guess I'll just try that in software later on, different values, is whether there needs to be a delay between me stopping the carriage or the time between me sending a pulse to the solenoid and the hammer actually actuating. So the question is, how long do I have to wait after the solenoid pulse before I move the carriage over to the next character? But I think I'm just going to do that on trial and error. One side note though, when a machine boots up, it does a little sanity check, and that's when it drives the carriage to the complete left, to the far left, and then to align the character wheel, the daisy wheel. It requires this switch to be shortly, so this limit switch to be shortly engaged after power on. It needs to be so for the machine to not throw an error. So if I was to turn it on right now, you will see nothing will happen for a bit, and then it'll start beeping at me. There you go. And I won't be able to test anything. That's because I'd have to short the switch a bit after boot up, so things would hit the left. Then need to wait for a bit and then release it again. Then it'll start up normally, even if no motors and stuff are connected. While digging around, I found yet another one of my really old microcontroller boards or designs. This one here is a 4-channel audio switch, so 4 inputs, 1 output, and you can simply select using 2 buttons here on the front. And you can see a current channel here. It will remember it over power cycles. That's about did feature-wise, and I think I also implemented this on an ATmega8, so let's open it up and see what I did back then. I remember the analog circuitry is absolutely horrendous. I'm just using a single transistor to switch the audio signal. So yeah, here we can see it. Actually not as dirty as I thought it would be, just in terms of the looks, but down there you can see these 8 transistors. They're responsible for switching the audio signals, and that's kind of ridiculous. But surprisingly enough, it did work, and back then I wasn't enough of an audiophile to notice, but distortion must be really severe. I'm not going to measure it, but yeah, that's how it looks like. And yeah, what I'm intending to do is steal the AVR out of this, because as I said, I need one, and I don't want to kill the LED cube. Actually, you know what, I'm not going to try. I'm just too lazy to hook this stuff back up and hook my scope up to it and everything. I'm just going to, there's an easier way to find out the maximum typing speed, and that is I'm just going to issue, I'm just going to arm the hammer in a fixed interval and see at which interval it stops working, or it only, it should fire it should fire 2 times, and then it only fires every second time, or when it starts to glitch, stuff like that. It's going to be easy to find out, and as I said, the rest of the values are not that hard to guess either.